Okay, thank you very much. Thanks for the opportunity to speak here, and thanks for the invitation. So I'm going to tell you some story about open curve counts, and there is some kind of problem with open curve counts that we overcame in joint work with Vivek. And as it turns out, there's some kind of wall crossing problem. I'll try to explain. But that wall crossing can also be used as a tool to calculate things, and there is a very rich structure emerging somehow. So some parts of this story that I'm going to tell you will look extremely familiar from kind of physics point of view and maybe also from math point of view, but some parts are not perfectly in line maybe what has happened in physics over the last many decades. So and I would like to encourage people to look into that somehow. Okay, so anyway, so I'm going to start out by telling some part of a standard story. So I'm going to start with a three-dimensional Calabi-Yau manifold, and I'm going to try to count holomorphic curves in that manifold. And from point of view of physics, then what we're doing is we're doing topological string. And this topological string is here defined by some kind of path integral where the action is kind of supersymmetric extension of this Dirichlet energy, okay? And so what do we integrate over this phi? It's a kind of triple, or maybe psi. So this is a map from Riemann surface into X. This is a vector field along S, and this is some kind of complex antilinear differential. So kind of formal derivative of the map U in some sense, okay. And then somehow this Dirichlet energy is just this component, and these components are there to get supersymmetry. But the main theorem in this business is telling you that you can actually forget some of this path integral pretty quickly, because the path integral by supersymmetry localizes. So this integral localizes on holomorphic curves. And you can forget about these extra fields. And so, so you have some kind of moduli space. And formally, we have this Gromov-Witten is equal to, well, the integral over the moduli space instead. But this dimension in the Calabi-Yau case of the moduli space is n, so this is dimension of x, complex dimension of x, minus 3 times the Euler characteristic of our surface, plus, so this is the general dimension formula, and it will tell you why this Calabi-Yau case is so nice. So this term goes because n is equal 3, and this one goes because we have the Calabi-Yau condition. So we see that this manifold M, the kind of moduli space where this thing localizes, has formal dimension 0. So if we wiggle the equation a little bit, this integral is just becoming a sum. So this kind of, this just a sum over maps in this moduli space, and then we have to count them, and typically one would think that they count by plus or minus 1, but they're kind of these are orbifold points, so it could be some rational numbers, and then maybe it's some kind of, so we were counting all disconnected curves, so I guess the count is something like that, okay? So, and at this point you can somehow now, at this point is where typically mathematics enters the picture. So mathematicians don't do this path integral, but they understand, okay, there is this moduli space, we can sum up things over it, and so this would be kind of the mathematical definition of Gromov-Witten invariance. But so now we can check invariance of this C W. So in physics, that invariance should come from kind of invariance of this topological string. But now in math, we can think about how does this invariant actually work. And so what we do is we we deform. So first of all, in order to get this moduli space be zero dimensional, you have to perturb the equation, and that's a kind of a big. That's not very easy because you have to do it compatibly over the space of domains. So there's a lot of work going into that. But assuming that you can do so, we can study this invariance by looking at one parameter families of perturbation data. So we somehow fix some perturbations so that this manifold, this orbifold is zero dimensional, and we count up its points. So, of course, really there should be rational weights on these points. And then as we evolve time, and if we pick things generically, one would somehow hope that this thing develops as a one manifold, and if we cut it over here and we count the ends of this one manifold, which are orientable, then the count over here is the same as the count over here. So this would be the invariance of Gromov-Witten invariance. But we have to be kind of a little bit careful, because in the compactification of the space of maps, there are not only smooth domains. So what can happen? So model model of possible non-compactness, so to say. Yes. Yeah, there is a there is a little W on all of these branches. Not the the degree. So you can weight this by the degree. That's right. So you can take some kind of T2 homology, and this thing kind of works homology class by homology class, or you could take all of them. Well, that's right. So you can certainly do that. Thanks. So what might go wrong with this argument is that as you study this thing in families, it could be that some curve, which initially looks smooth and nice, converges to a non-smooth domain, and then in the moduli space itself, it's problematic to kind of go on with time, and then that could be a problem. And this basically domain is modeled by some equation like this in C2, right? So in C2. So you take x times y equals to some kind of complex parameter epsilon, and you look at how this curve degenerates, and that's somehow, of course, well known. We have this thing going to the cross. But when we go out of the cross, then we have a two parameter. So this epsilon can be chosen freely among the complex numbers, and in a more suggestive picture, when you rescale the domain a little bit, you rescale the neck here, there is a neck length, and there is a rotation. There is a rotation parameter, right? So you can stretch and you can rotate. But that means that this disastrous moment is codimension 2. So the correct picture of this straight t-axis here is that, imagine that you choose it in a bad way so that you run right into this moment. Well, of course, you could instead go like this, right? And then you don't have any splitting, and this should be kind of a nice cobordism. So of course, so what we're seeing here is that things could, be born and then cancel again and so on. But these bad moments not going to happen, and that would tell you that whatever kind of complicated perturbation scheme you invent, which may be hard to understand, this count is going to be invariant, because you can somehow connect the data in a way that does not involve any bad splittings. Okay. So now I want to turn to the open curve case where this of course is not the same anymore. So the starting point for the open case is exactly the same. It's exactly the same path integral with the same action, and it again localizes on holomorphic curves. Okay, and what open case? So what do I want to say? I want to say that we fix a Lagrangian and in this X, and we look at, here's our L, and we now look at holomorphic curves which is allowed to have boundary, and the boundary lands in this Lagrangian. Okay, so so again we can try to do this path integral, and again it will localize on holomorphic curves with now boundary on this Lagrangian. So again we consider this sum of, so let me just not write everything out. I'm going to write it like this. So the kind of corresponding sum. And then we try to run our same invariance argument. And so we now have to look at this. And okay, we hope for the best, but now note that for curves with boundary, the model is not correct like this anymore, right? So for curves with boundary, this epsilon lives in R, right? Because you kind of want to take half of it, and so this is now an actual picture. And therefore, it's not going to work. So now, so the main message is now there is wall crossing. So in other words, we can have a curve that does exactly that, right? So somehow you, if I find so this is a picture of the boundary of the curve in the three-dimensional Lagrangian. So it's somehow, there's a little neck here, and just like before, there was this neck, but and before, when I glue it up, at least I can choose some kind of twisting between these two pieces. But now, you know, the half of the curve is determined. It should have its boundary in L. So this little neck is stuck, and I just have this codimension one thing, and in the limit, I go to this nodal curve, which has a boundary node now. Okay, so if I, for example, try to count these curves, then I count some, you know, this could be one disk. So maybe this is the boundary of a disk, and then when you break into two disks, right? So I'm not doing really well on my invariance. So somehow it can jump. And so there is no kind of naive invariance, but there is a way out, and that's to look back at what happens here. So when we go to this point, we can look at the normalization of the curve. So it has two branches. We can forget that it somehow has a node here. We can consider the two branches on their own, and then that moment is the moment in another one-parameter family, which where the curve crosses through itself, or two components of the curve crosses through on the boundary. And so, if we could now somehow identify these things, we could save the count, the count, and make it invariant. So let me draw the correct picture up here. The problem we had and the cure. So we have the time, again time, and then we have our problematic moduli space, which ends someplace here. So I'm drawing the boundary, and here we end at this time. We have this nodal curve. But we have another moduli space which just continues straight through, and it's somehow this normalization of this. Maybe I put some arrows here, so orientation of the boundary. Here it crosses through again, but then it crosses over. So if I now impose the relation that this curve minus that curve is equal to, and let's sort of encode the Euler characteristic. So this is maybe Euler characteristic chi, and this is Euler characteristic then chi minus 1. So if I I want to say that I do this, where I count my curves, I upgrade and I throw in some genus parameter, which I call z, and I count it by the negative, the Euler characteristic. Then you see over on this side, I have contribution from that curve plus this one, so that would be this plus that, I guess. And then when I go to the other side, I have only that one. But if I impose this relation, that I count the curves like this, then the thing is going to be invariant, right? And then the count on the left-hand side is the same as the count on the right-hand side. And now for those of you who ever studied knot theory, you see that this thing that we impose is called the Skein relation in knot theory. So if you have a link in a three-manifold, you can generate some kind of Skein module, which is generated by all isotopic classes of links, modulo this relation where you say that the links outside the little ball in the three-manifold are the same, and inside this little ball you're allowed to kind of change them like that. Okay, so this is somehow the first Skein relation. And let's check where is the second Skein relation. It comes from the second way that this curve can degenerate. And so we need to think what's about that. So there is another wall crossing, and that wall crossing, maybe I can also draw here. It's slightly different. So remember what we just did was kind of this, the answer to this one, when this was a real parameter going to 0, right? But in the complex world, that thing is equal to, it's the same thing as that thing, right? When you have I, you can factor one out. But in the real world, it's not. And so we need to understand what's happening at that moment when the boundary shrinks. And we have a kind of very similar pictures. We have our deformation. We have a moduli space where this epsilon is going to 0. So we have on the Lagrangian, I'm going to draw a picture here. We have a circle, and we have a kind of holomorphic curve which has the boundary of this circle, right? And then it goes out to the Lagrangian. And as we go to this moment, the boundary shrinks, and our holomorphic curve is intersecting the Lagrangian at one point, right? So the holomorphic curve is two-dimensional, Lagrangian is three-dimensional, and then we live in a six-dimensional space, so this is somehow exactly like the crossing on the boundary. It's a non-generic instance in a one parameter family, and so I can find the counterpart of this thing, which is just some kind of holomorphic curve. That's the one that when I don't have a boundary here, and it's at this moment exactly here. And then it's hard to draw because we're lacking some dimension, but it's crossing through the Lagrangian. So it's somehow exactly like this, but it's two dimensions and three dimensions and crossing through, okay? So now the question is, how can we compensate this? And the answer is that what is changing here, and we need to discuss how to measure that, but what is changing here, if you think about this moment, is a linking number between the Lagrangian and the holomorphic curve. And that linking number we typically count by variable a. So again, we have here moduli space of Euler characteristic chi and chi minus 1. And now we impose the relation that, so this is, we will count by some kind of a, the linking between u and L. So I need to explain how this works, but the key point here is that the linking jumps by 2, and we require that this the linking change is compensated by birth of an unknot. Okay, and you see that this is the second Skein relation, which is normally written like unknot is equal to A minus A inverse over Z in the knot theory literature. So that's kind of normalization of HOMFLYPT polynomial. So we see that if we kind of impose this HOMFLY relation, then this curve count is becoming invariant. And there is one kind of problem we need to address, and that's that this linking number is a little bit ill-defined, because what we are trying to do, if I'm kind of so imagine, for example, you take, let's put ourselves in R3 and take the z-axis, and then we can take some kind of curve that goes around. I don't know how it goes around here, but it doesn't matter. So now we can talk about the linking number between these curves, this curve and this axis, right? That's kind of, you see how many times it wraps around. But we're trying to do something similar, except that we don't have a kind of closed curve. We have some person who has its endpoints on the thing with which we want to link with, right? And then, of course, we're facing some kind of problem. We need to find some way of pushing this person off before we can sort of say what is the linking. And so I'm going to explain how that works, and then what then this A means. So in order to do that, we will use a four-dimensional chain. So we assume there is a four chain C such that this DC is twice L, and then we'll do something funny. So we need to relate this chain with the ways of pushing the map off of L. So, for example, and this four chain we shouldn't think of necessarily as a compact four chain. It will exist in cotangent bundle in all the examples and so on. So don't worry too much about this homological condition. But locally we need to understand how it works. So we will require. So here is L, and we're going to fix a vector field along L. And we will require that our curve, our four chain is smooth along the boundary, and it has inner normals J times V and minus J times V, where J is the complex structure in the ambient manifold. So we fix such a vector field, and then we impose further somehow genericity. Exactly not what I'm supposed to draw. So further genericity of our holomorphic curves. So we require, which is also generically true, that they're nowhere tangent to V. So the tangent vector and V spans everywhere a plane, and then the plane has a normal, and what we are going to do is we are going to shift the curve near the boundary along J times this normal, okay? And when we do so, then near the boundary, what happens is we have this four chain going off in direction J times V, but we have the curve going off, I don't know, whatever the curve, in direction J times N, which is different from J times V, right? So therefore, near the boundary, they don't intersect, and we can count intersection numbers with this C and U. So that tells you what this A is. So to kind of summarize, what we want to do is we want to count this C, and we take all the curves, whatever their weights are, then we take Z to the minus Euler characteristic of the curve. We take A to this linking number of U with L defined in this way, and then we take the boundary of U, whatever remains, and we think of it as living in the Skein module of L. So that means we encode the isotopic class of the boundary, actually frame the isotopic class, modulo these two relations and one more relation that I need to tell you about, but that's the standard relation. So the third relation is that this little piece of the boundary, if I have a twist in it, then that's the same thing as A times no twist. And so let me explain where this last relation comes from. So this last relation comes from the following, that when we have this 4-chain in one parameter family, nothing needs to go wrong with the curve, but the tangent vector could, at some instance, be parallel to this V, right? So here is our curve. But what happens then when I move on is that it's no longer the case, but there is born an intersection here. So if I were to project along V here, then I see something like this, that this bad moment, the tangent vector here, is equal to V. So this V is out of the blackboard. And say before that, it looks like that, and it looks like this, but there is a new intersection with the 4-chain. And so that means that we are also we get this relation for free. So therefore now, if I count my curves like this, I get some kind of invariant count. So whatever I deform, then it's gonna work. And you should realize just that somehow this invariance is some kind of very non-trivial process. So if I have some kind of Lagrangian, and somewhere I have my holomorphic curves, and they look like the boundary looks like some kind of trefoil or whatever, then as I deform the data, this knot may very well change very much. And for example, it could be a crossing change here. So whatever the crossing change, it could be a crossing change, and then there's a splicing, and so it's a somehow very complicated story about all these knots that develops as we deform the data. But if we're careful and compute the things in the Skein, then the result is still invariant. So let me now try to use this in one of the basic cases that somehow will also tell you how I plan to use this thing to actually do concrete curve counts. So we'll do some less concrete curve counts, but we start with something very concrete. So I'm going to look at the toric brane first. So toric brane, yeah. Yes, so there's an excellent question. So we are doing the following. We are doing virtual perturbations, but we are doing in a non-standard way. So the point is that if you want to impose these relations, you need to control the solutions, the relation between solution of one Euler characteristic and another one. And yeah. No, virtual class, yeah. No, it's in, yeah. Okay. Yeah. So, yeah. So, okay, this virtual has some virtual use. But anyway, what I want to say, what's non-standard is that we do not perturb curves of zero area. So that requires a lot of more work than it you cannot just take the usual Gromov-Witten perturbation and put it here. It's not going to work. So we do some kind of special treatment. We perturb out multiple covers by these perturbations, but we don't perturb out basically attaching constants to the curve then. So multiple covers are perturbed out, and then of course a lot of work to show that that actually works. And but we do that. Yeah, but after we perturb them, they're not there anymore, right? So somehow. But indeed, so that's let me explain this. I think it's going to be clear. So what happens here? So I'm going to do the toric brane in C3. So we take this C3 with coordinates C1, C2, C3, and inside here there is some kind of Lagrangian cone. So Lagrangian, let's say T2 times S1. And what is it? It's the thing that in coordinates looks like this. So you can check that the alpha and beta are circle valued. So that's the T2 times R, and this rho is well positive real number, and this is somehow in the kind of this famous toric diagram. This is the Lagrangian that sits right here. Okay, so it's somehow a cone going down. Collapsing in the middle, but now you can it's a cone on T2, cone on T2. That's right. Maybe like that, better. So it's a cone, and we can in somehow we can move it a little bit without moving it at infinity in either one of three directions. And in this formula, it means that you take, so this rho is going from 0 to infinity, and you can add on any axis rho plus some R0, okay? So you see that now this circle does not collapse anymore when rho is 0, and then you upgrade this cone to solid torus, so it's now S1 times R2, right? So those are actual Lagrangians and they're solid torus. And what I want to do is now I want to count curves. Let's say, let's fix one of them. Let's fix this one, the first coordinate. I want to count curves ending on this Lagrangian, okay? And if you think about it and look in these coordinates, you see that there is an obvious curve, and there is somehow the only curve there is, and it's the disk in the first coordinate plane. So if you put this R0 somehow, then if you look in the first complex coordinate plane times 0, our Lagrangian looks like this, and there is this kind of obvious disk there, right? And then what we want to do is we want to not count just this disk, but we want to count all the curves. And where are they coming from? If we think like Gromov-Witten theory, then you could take anything and add the constant curve at any point. And maybe more interestingly, you can look at any Riemann surface that branch covers this disk in some way, and so somehow you see that thing is not generic because you can move the branch point, so it's too high dimension. But what we're saying is that if we take this, not virtual, but the actual perturbation scheme, we perturb it, then we would get a whole slew of knots in here with the boundaries, and we could kind of count them and get some result. And I'm going to explain to you some very slick way of counting these curves. And this is the way that I think should be. So this picture, of course, extremely familiar from physics. But this way of counting the curves, I think, maybe not equally familiar. So, yes. But I claim I get it in a better way. Okay, and also I know what I'm computing. But anyway, so what I'm going to do is I'm going to look at this solid torus, but I'm going to look at it at infinity. Okay, And at infinity, all these independent on wherever R I put here, 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 they all look the same. Right? They look like this cone. And at infinity, this Lagrangian L, if I intersect it with the boundary of C3, so I take some kind of huge radius S5, then this is limiting to a Legendrian. It's called Legendrian submanifold. So, or if you wish, it's exactly this R invariant Lagrangian, okay, where I quotient out the R. Okay, so that, and this is a T2. This is a T2. And on this T2, I can look at curves. So look at holomorphic curves. With punctures. And these punctures have a very natural place to end, and at what's called Rabe chords. So let me try to tell you what that is. So we have on the C, so this is my S5, and inside this S5 sits kind of a compact part of C3, and just a standard coordinate outwards vector field, let me call it V, has the property that if I take this Lie derivative of the standard form, then I get the form back. So this is called Liouville field, okay? And if I take this Liouville field and I multiply it by J, then this JV, that's equal to the Rabe vector field, okay? So if you imagine that out here at the boundary there sits my lambda, and I have a flow line of this Rabe vector field, then the strip, if I just extend it by the R, so kind of Rabe chord times R, that's holomorphic out at infinity, right? Because it's somehow a complex linear tangent plane. And it makes sense, so this is what kind of symplectic field theory is about, so it makes sense to look at holomorphic curves of the following shape. So I take some curve, and at infinity I should draw it in this picture really. So yeah, so it's hard, but I'll try. So I have a curve here, boundary is following lambda, and then as I go out to infinity, I'm exponentially asymptotic to this trivial strip going out there. So schematically it looks like this. So here is kind of some Rabe chord, and here is boundary on lambda times R, and inside, of course, in this C3 still, okay? And now, as it happens, we said that these curves that were just purely inside here, they had all dimension 0. And these curves, they have, so dimension 0 kind of from the inside plus some kind of grading of this Rabe chord, okay? And in this case, one can show that the Rabe chords of this particular lambda, I mean we can draw it and so on, they can be organized so that there is one Rabe chord of index 1 and everybody else of bigger index, okay? And so let's see, I'll draw this Legendrian in a second, but we have one Rabe chord of index 1 and all other of index bigger than 1, okay? So, and in fact, so a concrete, so kind of, so I don't expect that you should understand this picture, but I'm going to draw it anyway. So this is some kind of picture of lambda, called front projection, and our Rabe chord is here. So just in order to kind of show you that this is nothing very kind of fancy or abstract, you can isotope it to somewhere where you know everything about this lambda. Okay, so moreover, we can determine the moduli space of all such curves very easily. So it turns out you squeeze this one and use some kind of Morse theory. So we can say that the moduli space of this kind of curves with one puncture at our chord C, maybe I call it C, that moduli space contains three components. It contains 3 disks. So, and they come with signs because of orientations. I'm going to draw them like this, but I'm going to explain to you by drawing their boundaries on this torus. So I'm drawing 2 points. What are those points? So those are the end points of the Rabe chord, okay? And then I have to draw the boundaries on this torus. Really, they kind of go off to infinity, but my infinity is somehow suppressed in this picture. So if I draw something like this will be one of them. Is this one? So what does it really mean? It means I go like this, but then I kind of go asymptotically up here, out. But this is what it looks like. And then I have another one, which goes around and comes back here. That's the 2. I have a third one which goes along the longitude 3. Okay. So and those these are somehow very easy compared to counting all these curves inside and perturbing and whatnot. It's just somehow some diagrammatics, holomorphic curves reduces to Morse theory in certain limit, and you can control this thing. And there are 3 disks. So now let's see what we can use it for. It turns out we can use it to just compute all the curves inside. And let me tell you how it works. So for that, we look at this one-dimensional moduli space. So you look at the one-dimensional moduli space. This MC, so it has this curve at C. So here, what I'm drawing here is I'm drawing the curves. This should be MC at infinity. So this is in the R invariant region as I kind of flow out all the way, okay? But now I'm looking at MC in C3. So this is somehow this is in S5 times R, okay? So out at infinity. And and I want to take the boundary of this moduli space, and I want to take the boundary of this moduli space if I consider it as valued in the Skein, just like when we count the curves, okay? And so I take any such curve. It's some, so maybe I'll draw it here. It's some kind of curve that looks whatever it wants, but it has one of these positive punctures. Maybe it has some genus inside, I don't know, some kind of maybe another boundary component, I don't know, whatever it is. So, and then I kind of let it, I know that it's one-dimensional, so it sort of propagates, and it may skein and, break and whatever, but none of that changes my count. It just looks like cobordism of this moduli space when I take it valued in the Skein. So nothing happens, and the only thing that kind of where it ends is when some part of the curve travels to infinity. The rest sits inside, okay? But we know exactly the 3 ways it can travel to infinity. So the boundary of this moduli space has to be equal to the first curve times whatever is the times z. Maybe I'll put here c, minus the second curve times c, minus the third curve times c, okay? Where c counts all the rigid curves, right? And the boundary, as with any one-dimensional space, if I take all the boundaries and sum them up with signs, then that's 0, okay? So I found a very interesting relation. I found 3 curves at infinity that when I look at them, in the Skein of this thing has to kill this partition function, counting all the curves. And actually it allows me to just compute what it is. So So for that one needs to understand some knot theory. What is this Skein module of the solid torus and so on? But that's well studied in knot theory. In Chern-Simon's language, it would be we need to understand all the line operators in a solid torus somehow in the large n limit. Okay, and so the Skein of this solid torus where we're computing things, that has a basis. Maybe I'm lazy, so I'm going to talk about the positive Skein. So what does it mean? I take a solid torus and I take all the curves that wraps positively, at least non-negatively, around the S1 in some orientation. Of course, my curves that I had, so now the picture is gone, but my curves, they all originated from these disks. So of course their boundaries will all kind of wrap positively, so I don't have to care about the negative part. So this positive part has a basis, W lambda, corresponding, so with one element for each partition, lambda, which are eigenvectors of the operation, let's say, meridian. So I'm going to explain meridian at infinity. I'm going to explain what I mean by that. So if you have so I'm going to draw a solid torus. I'm drawing a torus, and it's solid, so it's the inside of this guy. And then inside this solid torus, I have some kind of link going around. Then I can form a new link by acting with this one on the meridian at infinity. So that means that outside of this thing, I can surround it. I can add a new component like this, right? I take the meridian, I add a new component, and I get a new link. And that means that this adding the meridian is an operator on the Skein of the solid torus. And as it turns out, this W lambdas is an eigenbasis. So you can see, for example, if you go once around, you can splice and pick up, and you pick up maybe some A or something times the old curve. So they're eigenvectors. And now these three curves, I can somehow, to connect back to the formulas, I can pick some way, maybe this way, of connecting the curves up to closed curves. And then you see what I find that the recursion relation, this moduli space relation that I find, is actually like this. So it's the unknot, which is just multiplication by a number. So I'm going to write it in some notation. P00, so that means the curve in this torus at infinity goes around nothing, minus P10, so that's the meridian, minus, and there is some A, but let me forget it for now, 0,1 times this Z is equal 0, okay? And if I now write up this Z in some kind of, in this eigenbasis of this operator, you see that the only thing I need to understand is now how this one is sort of pushing representations forwards. So this is a perfect recursion relation for determining all these C's. You start in the empty one with 1, and then you kind of go on. And what you find is that this Z is equal to sum over all these partitions. And then some formula which looks like the following. So I'm drawing my partitions in this standard way, like whatever these diagrams are called. Box in lambda, content polynomial, content of a box, which is the co-arm minus co-leg, and then q to the hook minus q to the minus hook. And then times this w lambda. So hook is, well, hook, better box for hook is that. So it doesn't matter so much. But anyway, so you see we get some kind of explicit count. And as you say, this is the same count as Aganagic Wafa if you translate in the right way between the two. But here, in some sense, we know where we are counting. So it means that I'm asking the question, what is my Skein valued curve count? Well, if I look at all the curves that kind of have the boundary in this W lambda, then the count is this coefficient in front, right? So this is kind of very sharp statement. But also, it tells you that this this whole thing is known by this relation at infinity. There are three curves at infinity that knows everything about everybody inside, right? So it's some kind of very, very drastic statement, and it's the yeah, exactly. So I'm going to cut a few. I wanted to talk about knots and links and so on, but I think I'm going to stay in this example and do things here, and then knots will have to leave for further discussion. So yes. Arbitrary size, every size. Say again? Yeah. Yeah. This is already it is already a large n. Yeah. No, you're correct. I'm already in the large n limit. No. Oh. Well, okay. Yeah. Yeah. So SUN scale will be set A is equal Q to N, right? And but somehow this theory works better with just A than with QN. So in some sense, all the kind of relations that you would get by setting A as Q to the N in this story would come as some kind of coincidence. It won't affect the curves. The curves will be the same, but some of them cancel, and some. So it's somehow, as I think what in physics language Vivek would say is that this theory really lives already at n is equal infinity. No, but it's just because you want to use some language that wasn't used, right? So somehow, if you approach this Skein from point of view of physics, there is no A, right? In Chern-Simons, there is no A. No, 80. Okay. I'm certain. I'm certain that it is. Okay. Anyway, okay. So now let me say something about this quantum curve and so on. For this brane, there is a kind of what I would call augmentation curve or mirror curve or something like that. So it's this curve, right? That somehow, if you want to get the Wafa mirror to this thing, you take this curve and you take conics degenerating over it, right? So this is the curve. But then, as you say, you can upgrade this into quantum curve, which now acts on, maybe I call it C symmetric, because that's what it is in this case. So if I restrict this lambda to only symmetric representations, then I get the power series in some variable, x, for example. And indeed now these operators, where x, y hat is I guess Q inverse or whatever it is, y x hat. So this is the quantum torus that we heard so much about. So there is this, so we start with a curve and we get a quantum curve. And what we have here is a kind of, so this is a first lift and there is a second lift which goes from symmetric representations to all representations, and now our curve is instead valued in the skein of T2. So this, of course, is the kind of U1 skein of torus, and this now becomes this full HOMFLY skein, and we have such a relation. So, but, and that's the kind of question that I was aiming for, but now I have to pose only in this restricted setup, but it's a kind of interesting question. So what happens here is that you can look at, if we start in the first case where we have the curve and this relation. So then there is a kind of D module over this curve, which just it's kind of Weil algebra divided by this ideal generated by that operator. And from that point of view, what does this wave function do? It gives you a map from the Skein module, or from this operator algebra perhaps, divided by this ideal. So this is the D module, into just regular functions on X, right? So that the power series in X. And it just takes 1 to Z, right? And then the fact that this one kills Z, then somehow that's what it is. So, but that module sort of lives naturally over this curve. You could express regular functions in X or Y or whatever kind of coordinate you like, and that's the point of these D modules, that you can somehow, I mean, they behave well under coordinate transformation. Now, for the case that we are looking at here, we have a similar story. So we now have a Skein D module, which in this case is a quotient of this skein of T2 by our operator ideal. And now again we have a map from this Skein D module over whatever it is into the skein of the Lagrangian where we count the curves. But just as this kind of coordinate which gives us different regular, I mean, not different regular functions, but regular functions that are parameterized in different ways. In this case, we somehow have one Lagrangian here and one other Lagrangian here and a third one here. They all have the same topology, but they're not the same. Yes? T2 times R, sorry. So it's basically all these curve classes with some commutation relation. So, and then I divide out by this guy, and so now I have the same thing. So I take one in this one here to the Skein valued partition function. Yes, and somehow that's somehow the question in general is how well, or is there any, I mean, physics reason, other reason that this picture always work like that we have this, we can think of whatever this curve is, augmentation curve, mirror curve, as a moduli space of Lagrangians, and these Lagrangians should always be sufficiently good that you can make sense out of their skein. Maybe they have some intersections or whatever, you have to find the right type of skein so that you somehow have the right, I shouldn't probably not say sheaf, but it looks like sheaf, or maybe it's co-sheaf. but over each point here, you have some Lagrangian, you have such a map, and it behaves well under moving around in this in this augmentation, right? So it's some kind of lift of regular functions to skeins on the Lagrangian at the point, right? And I think that it would be, if I were not saying skeins, if I say line operator, I say such a thing, maybe there is an incarnation of this somewhere in physics, right? And also there are these kind of line operators, very heavy people at infinity that seem to know everything about what's inside. So I'm going to stop at it. I'm sorry I got stuck in this one example. I had a few more, but maybe Vivek can say something about them. So I'll stop at this. So thank you very much. Yeah, whatever governs topological vortex, yes, you can relate them to that. And this one knows more. No. This quantum curve, the first one knows basically only about the symmetric representations. And this one knows about all representations. So in the forbidden world of talking about brains, then you take many brains, and this would be kind of the symmetric ones, and these would be all sure combinations. No, is that? It's much bigger, so yeah. Yep. The, that I don't know. I mean, you're asking about how to kind of do kind of HOMFLY homology. Yeah, I don't know. There is some kind of very interesting story that in this case is very simple. So basically, in more experimental work, what we found about this kind of HOMFLY homology is somehow it's the case that in this case, very often, so in this case, this count comes from one disk. And there is some kind of work for knots and so on where also HOMFLY counts comes not from one, but from many disks. And what it seems like is that, at least in simple examples, some of this HOMFLY business is related to refined count of these disks along this with kind of this T parameter and some U1 actions on. I don't know how to make complete sense out of that, and I don't know of a kind of truly homological theory that does anything there. So in our world, it's as if you're doing some kind of Hodge theory and out comes homology, and there is no differential whatever. So I don't know. It's the true answer, but there are very tantalizing indications maybe that sometimes the HOMFLY homology, at least for the symmetric colors. So the other ones, of course, I don't know. Nobody knows, but that might be related to something like that. But I don't know. The kind of course, yeah. Yeah, everywhere HOMFLY Skein. Yeah, that's right. There is some story with Kaufman Skein when your Lagrangians have involution. You can more or less run the same. HOMFLY. Yeah. This is always HOMFLY. Yeah, that's right. Yeah. If you know this one, you can do. Yeah. A lot of stuff disappears, but you could do it. So if you know this one, you know everything somehow. This is the U1. This is the U1 HOMFLY, and this is the UN, all N. So to Q equal to. That thing, yeah, that's yeah. 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 So for no, you have to have some. So I would say that you can do a lot of this stuff for any Lagrangian, but these conditions with the chain and so on is some way to guarantee that what you get when you represent, that you find somewhere to represent the data so that's non-zero. It could be in some kind of crazy case that you have some Lagrangian which doesn't have such a chain or something, and you do the count and it's invariant all you want, but where it takes values is in zero or something like that. Right? So it's more. So the whole program always works, but it's also extremely interesting, especially for conormals of, like in this kind of Guriv alpha story, for conormals of knots, and also for other Lagrangian fillings of these knots. So that's where this curve that here is so nice, this curve, right? You can just one way. That's getting complicated, and understanding this sheaf of Lagrangians and that thing and this thing, and that's pretty challenging. And then one could ask, how much of this picture always goes through for knots and so on. And that's where we're fighting right now. For HOMFLYPT, it works like a charm, but HOMFLYPT is too simple. So. Yeah. Yeah, that's right. Yeah. And for example, then for the HOMFLYPT, you can do it. You have three very simple equations, and they just determine all the colored HOMFLY of the HOMFLYPT like a charm. But already for the trefoil, we don't really have this yet. But yeah, everything. You can. Yeah. That's right. So if you have a multi-component thing, then you'd have to take the tensor of the Skein. So that's right. But then there is also some kind of question which wasn't answered or was answered. I don't know. But you can also now ask, how do you go from a couple of U1s to UN, right? And that's a very valid question. And at least there is some kind of tools to try to answer. No, everything is infinite rank. Right? So it's all, we're already at infinity. So and then somehow the other theory is not so easy to make sense out of here. So somehow that's it. And in this example, it is equal. That is just yeah. Yeah. Okay. What do you mean? Yeah, for this one, it's easy. I mean, I don't know. You can calculate everything. Yeah. And I mean, I don't have like something I would write a paper about, but I have some intrinsic understanding. But you can see kind of how it works and who is who, which curve is which curve in the skein and so on. You can mess with it a little bit, but there is some. So there is also a. I think that count and many other counts will come from a kind of a certain universal thing which goes from ray orbits down to some curves. And if you know that kind of Lego piece, which you can probably calculate, we haven't yet, but if you can do that, then you can pass between whatever they call relative invariance and open invariance in certain cases, and then you understand something. But of course it's always tricky, because this understanding, whatever you understand, you should remember that you understand in this Skein module, right? So you draw maybe some nice curve that is the boundary of this and that, but in principle you have no right to say that that curve is better than any other curve related to that one in the Skein times some strange polynomial or whatever. So one has to remember that, but you can sometimes find kind of concrete curves, that's right.